Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Alif bin Muhammad Khalil, and the title for the project is an electric altering vehicle battery charger powered by PV array based on zeta converter. So the first thing we're gonna look is the plot diagram for the system. So this is the figure 3 show that the MPPT charge controller overall plot diagram. So what's the project gonna do is we want to charge a DC load, which is the lead AC battery, by the PV module through a zeta DC-DC converter. So the photovoltaic module will go through the zeta converter to charge the DC load, which is the lead AC battery, and the PV module also supply the voltage and the current to the MPPT algorithm for it to generate the duty cycle for the controller and give the duty cycle to the PWM generator for it to control the switching for the zeta converter. Next, we're going to see the PV array specification. So the PV array specification, the maximum power is 200.072 watt. The voltage at the MPP is 70.8 volt, and the open voltage is open circuit voltage is 22.5 volt, and the current at the MPP is 5.62 amp, and the short circuit current is 6.23 amp, and the number of cell per module is 36. Next, we're going to see the formula how to calculate D. So the V out is based on the battery, which is the 12 volt battery, and the Vs or Vin is equal to the voltage at the MPP, which is the 70.8 volt, and the D we're gonna get is the 0.4. Next, we're gonna see the parameter for the zeta converter. So this three formula is being used to calculate the inductors and the capacitors. So L1 and L2 must be greater than 0.6 millihenry, and C1 and C2 must be greater than 0.25 millifarad, and C2 must be greater than 3.86 microfarad. But the parameter that I choose uh, must be greater than this number, and the table here you can see all the parameter that I select, all the parameters that has been selected. Next, we're gonna see the flowchart for the PNO algorithm. The MPPT that I use is the MPPT algorithm I use is the PNO, which stand for perturb and observe algorithm. So uh, it will start, and then it will read the voltage and the current from the panel. From the voltage and the current, we're gonna get the power, the PV power, the power output for the PV, and then we're gonna set uh, the delay. So we're gonna get the P K minus 1 and P K minus 1 and V K minus 1, which is the iteration before it. And then we're gonna plus and minus both PK and PK minus 1, also with VK and VK minus 1 to find the delta P and the delta V. So we're gonna look at delta P. If it's equal to 0, then we're gonna end the flowchart. And if it's greater than 0, and we're gonna go to this road and we're gonna see the delta V next. So the delta V is less than 0, then we're gonna add the old duty cycle with the delta D. So the delta D that I've been choose is 125 micro. So if it's greater than 0 or equal to 0, then we're gonna minus the old duty cycle with the delta duty cycle or delta D. So if it's less than 0, if the delta P is less than 0, then we're gonna also see the delta V. So if the delta V is less than 0, we're gonna minus all duty cycle with the delta D. And if it's greater than 0, we're gonna plus it with the delta D. So basically it's just the difference of the mathematical operation. Okay, this is the overall circuit for the design. So the irradiance that I choose here, you can see the irradiance that will go into the PV module is the step signal, which means that it will be reduced 200 irradiance per 2 seconds. So at the first 2 seconds will be 1000, and then we reduce to 800 when it reach 2 seconds and until 4 seconds, and then we reduce again 200 until 6 seconds. So the simulation will be run until 6 seconds. Next, we're gonna see the PV module side. So the PV module side is follow this parameter. So you can see here the cell is 36, the upper circuit voltage is 22.5, short circuit 6.23, the V max is 70.8, and the current at MPP is 5.62. So we're gonna plot it to see the irradiance at 1800, 1800 and 600 irradiance. So from here, from the power versus voltage graph, you can see that at 70.8 volt, it will reach the 200.072 watt in power. And for the 800, we're gonna see that it must reach 161.786 power at the 17.9611 in voltage. Same goes for the 600 irradiance. The voltage must be 18.0342 at the power of 122.262. So we want to get the MPPT. So the power must reach the 200 for the 1000 irradiance, and must reach 162 uh, 161.786 power watt in 800 irradiance. Same goes to 600 irradiance. We must get the power 122.262 watt. Okay, and this is the voltage versus current. So at the voltage 70.8, we're gonna get the current equal to 11.24 at the 1000 irradiance. So that is the graph for the uh, PV module. So next we're gonna see the next is the zeta converter. So here is all the zeta converter. The original zeta converter is from have this element, which is the L1, C1, L2, and C2, the diode, and also the MOSFET. So the additional element is the C in, which control the voltage of the PV module, and the diode at the output before entering the lead acid. So the function of this diode just to avoid any current flow from the battery to the element or into the components inside the zeta converter. So we want a one-way flow of current only into the battery. So let's go here. Here is the P&O algorithm. So I translate this flowchart into the plot diagram. So if we're gonna read it gives the PV module will give the voltage and the current. So it will read the voltage and current from the panel, and we 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 multiply it to get the power. So the second step, we multiply it to get the power, and I put the unit delay here to get the iteration before. to delay it. So we get the P I minus 1 and P. And then we're going to get the delta P, which is the differences between these two. And then we're going to, so here we delay it and we're going to calculate the delta P. So we're going to put it into the switch. So the switch is equivalent to the condition here. So if delta P is greater than 0, so it's greater than 0. If yes, and we're gonna see uh, if it's greater than 0, so we're gonna see the delta V. So the delta V is here, which is I plus minus the Vi minus minus 1. So we got the delta V. So if okay, we're back here. If delta P is greater than 0, if delta P is greater than 0, yes, we're gonna use this rule. And we're gonna see if delta V is greater than 0. So if delta V is greater than 0, for this one is less than 0. So less plus, but it's greater, we minus it with delta D. So duty cycle, all duty cycle will minus with delta D. So delta V is greater than 0. So yes, it will be minus. So the gain here is minus 1 to show that delta D will go through the minus 1 gain, which will produce the negative delta D. So it will minus the delta D. So if less than 0, so it will be plus the delta D. Okay, and for same goes for if the delta P is less than 0, so it will be use this road instead. So you see the delta V is greater than 0. So delta V is greater than 0, we're gonna plus it with delta T. So it's greater than 0, and then it will plus with the delta T. And if it's less than 0, it will be minus with delta T. And then we're gonna plus it. So the output here will be the delta D that we have choose here, whether it's plus or minus. So if we plus it with the current duty, the old duty cycle, which is the Ti minus 1, plus with the delta D. So I put it here, the memory for the old duty cycle. And this is the saturation to limit the duty cycle. So I limit it to 0.1 until 0.9. So we will not exceed the boundary. And I put here another switch with the condition of P is, it take is here, which is P is must uh, P P is not equal to 0. Okay, if it's not equal to 0, then it will get the input from here, the delta, the P and O algorithm. It is equal to 0, then I set it to the 0.4, meaning that this is just to state the initial duty cycle for the system. Since the duty cycle that we need is 0.4 for it to step down the 70.8 voltage of the PV to the 12 volt battery, and then it will go through the PWM generator. So the frequency that I use is 24 kilohertz, as you can see here, and it will go into the MOSFET to control the switch. So next we're gonna see the simulation. I have already run it just to save time, because it takes a long time to run. So here is the first graph. Here is the PV versus the P out of the for the MPPT algorithm. So as you can see here, at 1000, it reached 200, which followed the specification of the PV module. So at 1000 it reached 200, and at 800 it reached 161, at 162 and power and a watt, and then at 600 it reached around 1 to let's see, it reached around 122 in power, watt. So we're gonna study the graph. Okay, as you can see here, the settling time for the uh, PPV, or the power output from the PV module, is around from this point. We're gonna use the ruler. So it is from 0 until this point, the setting time. So it's around 6.834 millisecond, or 7 millisecond. So the settle time for uh, the PV module to reach the MPPT is around 7 millisecond. Same goes to the voltage graph. This is the voltage graph, and this is the current for current graph for the IPV and I out. So the settle time for the PV module is 7 millisecond, and you for the for the out, I mean the out power out into the battery is around, let's see, so it is around 70 milliseconds for it to stable the output. Same goes to the I out. However, for the V out, since it depends on the battery, so the voltage is proportional to the is equal to the voltage of the battery. Next, we're gonna see the okay. This is the irradiance. Meaning that the the step the signal input into the PV module from the 1800 and 600 of the irradiance at the step time of 2 seconds. And this is, as you can see here, this is the SOC of the battery. So it is increasing, means that it is charging. So the battery is charging, and this is the duty cycle for the switching frequency. So as you can see, it is variance, means that it will keep variance because of to control the MPPT. So the voltage at the PV module will stay at the MPP, maximum power point, and the power reach the MPP, which is the maximum power point. So that's it for the P&O algorithm. I also run the for the open loop, meaning that uh, here you can see that there is no P&O algorithm. So the solar will go to the zeta converter and into the battery, and the MOSFET or the switch is being controlled by a constant switching period, which means that the pulse width or the duty cycle has been set to the zero point 0.4 duty cycle, 40% of the, or the 40% of the pulse width. So the duty cycle will be zero point 0.4, and this is the period, which is 1 divided by 35,000, which is the frequency. So this I also have run it. So you can see that it has not reached the MPP at 1000 irradiance, it should be reaching the 200 watt, and same goes to the 800 irradiance, it should be reach the 162 for the 600 irradiance, and for the 600 it must reach 122. However, this one almost reached, but it's not reach the goal of the MPPT. So I also have uh, combined these two graph to show you that okay, here this is the graph. We have PPV open loop, which is the graph before, and the P out overload PPV for the MPPT algorithm, which is the PNO, and P out of the MPPT, which is the PNO. Okay, here I can, as you can see, uh, this one is the MPP out and the MPP, the P out and the PPV for the MPPT. So at 1000 it reached the maximum of the power, and for the open loop, both of the PPV and P out have not reached, and it have a big settling time compared to the P out, and the power is also not it have a big, it's not it have a high delta P. If you can see, peak to peak is very high compared to the PPV and P out of the uh, MPPT algorithm. Here you can see the SOC of the battery for the open loop, and the SOC which is the MPPT. So you can see that here the SOC for the battery for the MPPT algorithm is much more greater than the SOC of battery which not use the MPPT, which is the open loop lah. And then this is because the current input into the current flow into the battery is much more greater for the MPPT. You can see here the IR MPPT. The current that flow into the battery is higher than the IR open loop, which is you can see here is around 17 for the IR MPPT, while the open loop is around 13 uh, ampere. So I put all the data inside a table for to see the efficiency and the difference between the specification of PV module and the output. So this is the comparison between open loop system and the PNO algorithm method. So the theoretical output of PV array, or the specification of the PV array, we can see it should be 200 watt at 1000 irradiance. So for the open loop, it just produce 166.18, and if we using the PNO algorithm, it reach 199.51. So all this value is the average value for each system. So for the 800 irradiance, we can see that the power is 161.79, while the open loop only produce 141.67, and the PNO algorithm is producing 161.60, which is really close to the theoretical output of PV array. Same goes to the 300 irradiance. So the theoretical output must be one theoretical output of power is 122.26. The open loop only produce 113.24, and the PNO produce 122.11, which is very close to the theoretical power output. So here is the efficiency of PV array output power. So as you can see, the efficiency of the open loop only reach for the 1000 only reach 83.06, while 800 is reaching 77.75, and 600 reaching 92.62. So the lower the irradiance, the greater the efficiency. But if the irradiance is much more higher, and from the pattern here, the efficiency will be dropping. So for the Peano algorithm, it have a good, a great efficiency. So as you can see, it's 99.72 for the 1000, and for the 800 irradiance, it reached 99.88. Same goes to 600 irradiance, which is 99.88. So we have a high efficiency. So the next table is showing the efficiency of zeta converter between open loop and PNO algorithm method. So we compare input power of the PV for each system with and without the MPPT. So for the open loop, this is the input power 166. For the output power is 147.78. So the efficiency is only 88.8 and 928. But with PNO algorithm, we can see that the input power, which is 199.51, is the almost give the output power same to the input power, which is 199.5. So the efficiency reaching 99.995%. So the input power is the power here, the PV, while the output power here I take it from the power at the load or the battery. So we can see the data for the efficiency. So for 800, and you can see that the efficiency increasing, but it's not reach. It's not. It lost to almost 14 watt for the 800, and for 600 it lost around 10 watt. So it have an efficiency of 90.118 and 91.814. But however, for the PNO algorithm, you can see that the 161.60 and the output power is 161.34. So it's almost the same. So it's only a difference of 0.26 watt. Which reaching the efficiency of 99.839 for the 800 irradiance. For 600 irradiance, we have seen that it's slightly greater. Here is the some error. It should be 99.92, and this is actually 99.92. So that's it for the simulation. Oh, I forgot to explain this one. This one is the battery controller. So the SOC, if it's less than 100, and it will give the output here 1. And if the V battery is less than 13.0658, it will give the output here 1 also. So this both condition is true. It give the output here 1. So it allow the duty cycle. And if one of the condition is not true, the output will be 0, and the new duty cycle will be 0. So this value I get it from the battery specification. So which is the fully charged voltage is equal to 13.0658. So I take it and put it here to control, to protect the battery from exceed the value of the fully charged voltage. So that's it for the simulation of the uh, for the system. Thank you.